This is question 7 from the second CSAT sample paper. So here we're looking at trees. That means we've got points and connections between them. And we'll say if this point is to the right of this one, then this is the parent and that's the child. And this is called a ternary tree in the question because there's at most 3 branches coming out to the right of each point. So we're told the first node has no parents. Each of these is a node, and there's one at the start, which is the start, so it has no parents, nothing to the left. The other nodes all have one parent, so we don't have any loops, for instance, where both this node and this node are parents of this node. There's only one parent for each node. And we're also told each node has 0 to 3 children, so we can have a node basically finishing, like here, or this one I've drawn with 2 coming off, this one with 3, these ones all with 0, this one has 2. So anything between 0 and 3 is fine. And now we're asked, what are the greatest and least possible depths with n nodes? So the depth is the number of layers of connections. So if we imagine there was nothing after the dot dot dots here, the depth would be 1, 2, 3. So if you want to have a go at this question yourself, pause the video now. Okay, so let's start off with the greatest because that's easy. We have n nodes and we want to make the tree as long as possible, as deep as possible. How do we do it? Well, we just put them all in a straight line. So we just put n nodes all in a straight line and connect each pair together. And in this case, what is the depth? Well, there's n nodes, so there's n minus 1 connections between them, so the depth is n minus 1. And the least depth, that's where it gets complicated. So what does it look like? Well, basically we want as many children per node as possible because that means we want to add children to all the nodes we've already got before we increase the depth. So we want each node to have 3 children if possible. They can have fewer if we've just run out of nodes to put in, but we never want to say, start with this, let this have 1 child, and then give that child itself a child, because we could have taken this node and put it up here instead. So we always want to fill up the nodes we've already got, so we want 3 children per node. We've got to figure out what that means for the depth in terms of n. I think in this case it's easiest to think about the maximum value of n for each depth, and then we'll think about what happens for in-between numbers. Because you can already see, just looking at this first one, if there's 4 nodes, we put 1 at the start and it's got 3 children, and that's fine. And that's the maximum number of nodes we can have for a depth of 1 is 4. But if we had, say, 3, then we'd have this starting node, and then it would only have 2 children, we wouldn't have filled it up yet, so the depth would still be 1. So you can see there's multiple values of n that give the same depth, the same minimum depth. So it's easiest to think about the maximum number of nodes for each depth and then work backwards. So let's do that. Let's list the depths and then the maximum number of nodes for each. So we'll start with a depth of 0. What does that look like? Well, it's just 1 node, or potentially 0 nodes. So the maximum number of nodes we can have is 1. And this is a tree, but it has 0 depth. Then if we have a depth of 1, there's at least 1 layer of connections. So I already said that's going to look like this. There's 4 nodes maximum. And then for 2, what's going to happen? Well, we just add 3 children to each of these. I won't draw the children on, but I'll draw the connections. So you can see there's going to be 9 nodes here, then 3, then 1, and that gives me 13. And for 3, I've said 40. Why is that? Well, because the next layer, if we had 9 here, there's going to be 3 children for each of them. The next layer is going to have 27 nodes maximum. So we add 27 onto this to get 40. So if we're trying to find n in terms of d, bear in mind we eventually want to do the opposite. We want to find d in terms of n. But if we are currently finding n in terms of d, what is that? Well, we've got 1 node for the first layer, and then 3 for the next, and then 9 for the next. And we're just adding all these numbers up to 3 to the d. Because notice if the depth is 0, we've added up to 3 to the 0 here, 3 to the 1, 3 to the 2, 3 to the 3, etc. So we're adding all the powers of 3 up to 3 to the d. And this is just a geometric series. So we can write down the value of this. It's going to be 3 to the d plus 1 minus 1 all over 3 minus 1. And then the bottom is just 2, so we can slightly simplify this to a half times 3 to the d plus 1 minus 1. So if n is the maximum number of nodes for each depth, the value of n is this. But now we want to work backwards to find d in terms of n. And bear in mind, n could be any number. It doesn't have to be one of these special numbers as a maximum. So the first thing we'll do is we'll rearrange this to get d in terms of n, where n is a maximum, and then we'll think about what happens when n is an in-between number instead. Okay, so I'll start with this formula for n we just found, and now we want to find d. So first of all, let's just multiply both sides by 2 and add 1, so we get 3 to d plus 1 equals 2n plus 1. And now we can take logs of both sides, and then take away 1, and that will give us d. So I did this with log 3 just to keep it simple. So we do log base 3 of both sides, we just get d plus 1 here, this log on the right, and then we take away 1 to get d. So d is this when n is a maximum number of nodes. So if n is one of those numbers we're looking at, 1, 4, 13, 40, etc., then this will give a whole number. But if n is an in-between number where the last row of the tree isn't filled up, then what we'll get here is not a whole number, it will be a decimal. So the question is what to do if it's a decimal. Well, if it's a decimal, we want to round up. So suppose the answer is, say, 2.7, so between 2 and 3. So that says the depth is between 2 and 3, but the depth has to be a whole number. If it's between 2 and 3, if it's bigger than 2, that means we've passed the value of n that fills up a tree of depth 2. So we've gone on to a tree of depth 3, i.e. as soon as we go past 2, we just jump up to the next whole number. So for instance, if n is 4, that gives us depth 1. If n is 5, that means we have to have gone on to the next row, so we have to have gone up to depth 2. And if we stuck in n equals 5, then we'd get an answer between 1 and 2, and we round that up to 2. Because as soon as we've gone past depth 1, we have to go straight up to depth 2. So the main point there is that we're always rounding up, if d is not a whole number. So what does that make the answer for d in terms of n in general? Well, if you're a computer scientist, perhaps you've seen this notation before. We want to write, if this is an integer, we want to keep this, but otherwise we want to round up to the next integer, the next whole number. So I've written it like this, with these square top brackets. I could have written them around the whole thing instead, it doesn't make a difference whether the minus 1 is inside or outside. And this just means I've written it as the smallest integer, which is greater than or equal to x. So that basically means rounding up to the nearest integer. So if x is already an integer, then this function of x is just x. But if x is between two integers, say it's 2.7, then we want the next integer greater than or equal to 2.7, which is 3. And that will be the answer. So this is my answer for the least possible depth in terms of n.